Hello, and thanks for clicking on this Prenarculus production. Today, we're going to talk about logarithmic functions for the first time. So far, we've talked about exponential functions, and now we're going to take a look at how logarithmic functions relate to those exponential functions we've already talked about. Okay, so let's talk about something that all of you have been doing since you were very young: inverse operations. Okay? Every operation that you have learned in math has an inverse operation. From kindergarten through with addition, all the way through where you are today. Mathematics is really all about one type of operation and its inverse. So, for example, addition. Its inverse, well, that would be subtraction. Right? It undoes addition. Multiplication, you want to solve that. Its inverse, division. If I square something and ask you to solve it for x, how do you undo the square? You take the square root, right? Okay, so the inverse operation of squaring is the square root. But what we have and we're working with now is exponentiating. 2 to the x is equal to 10. How would I undo the fact that there's an x in the exponent? To undo that, its inverse operation is the logarithm. That's what we're going to talk about. Okay? We're going to talk about the logarithm. So, again, we're talking about inverse operations here. All right. Now, let's say I have an equation which we just worked with, y equals a to the x. Okay? We have y equals a to the x. That's an exponential function. If I ask you to find its inverse, you would tell me its inverse is, well, you just switch the x and the y. That's how you find an inverse, right? X equals a to the y to find its inverse function. This equation, x equals a to the y, is a strange equation. It's not solved for y. It normally would be, right? That's how we work with equations. They're normally y in terms of x. They say y equals. So the inverse operation is the logarithm. And the logarithm, instead of writing x is equal to a to the y, we can also write y equals log of x with base a. And this is an example of the logarithm. Okay? This is what a logarithm is. That's what it does. It is the inverse of the exponential function. So let's talk a little bit about what we just talked about here. So a logarithmic function, just as we can write a number in fraction form, we can write it as 1/2, or we can write it as a decimal, 0.5. We can write equations in both exponential form and log form. So that's what we just had a moment ago. If we have an equation that says a to the y is equal to x, you can write it in log form as y is equal to log of x with base a. Okay? These two forms are interchangeable. That's one of the most important things you need to understand about logarithms. If you can't solve a problem in this form, 95% of the time, if you switch it to this form, you'll be able to solve it. So you can go one or the other, your choice, whichever's easier to work with. All right, and now we have a couple of special logs. If the base of a log is 10, so if a is 10, we refer to it as the common log. And we can write the log without the base. So log of 2 just means log of 2 with base 10. If the base of the log is e, that number 2.718 that appears in applications all the time, we call it the natural logarithm. And we write the log as ln2, which means log of 2 with base e. We call it the natural logarithm because it's the easiest one to work with in calculus. It's the easiest of the logs to work with. So if we write ln 2, that means log of 2 with base e. Okay? All right, so let's see what we can do. Let's start by converting from exponential to log form. So right now, this is in an exponential form. I want to write it in a log form. So we have a to the y is equal to x will become log of x with base a is equal to y. So what you need to understand here is that if I want to write this as a logarithm, we're going to write log. The base of the exponent becomes the base of the log, and these two, the exponent and what they're equal to, will switch positions over the equal sign. So log of 9 base 3 is equal to 2. That's what we get. Okay, let's try 10 to the x is equal to y. So the base of the exponent becomes the base of the log, and then these two switch positions. So log of y base 10 is equal to x, or we could just write log of y is equal to x. We don't need the base 10. N to the a equals r would become log base n, r is equal to a. And then y equals e to the 5th would become log, e's the base, so e's the base of the log, of y is equal to 5. Instead of writing log base e, we can write ln for natural log. So the natural log of y is equal to 5. These are the 4 answers written in log form. Okay, so that's how you go the one direction. Let's go the other direction. From logarithmic form to exponential form, you got to be able to go back and forth between the two. So if I have log of x base 7 is equal to 2, the base of the log becomes the base for the exponent, and the x and the 2 switch positions. So the 2 becomes the exponent of the base, and then the x is what it's equal to. So 7 squared is equal to x. We're just converting. I know you can figure out 7 squared, but all we're doing is converting from one to the other. We don't have to figure it out. Okay, so log of y base 4 is equal to x. 4 is the base of the exponent. The x comes over, and the y comes over. 4 to the x equals y. Log of y equals 5. Well, log with no base, that means there's a 10 there that we don't see. So that's 10 to the 5 equals y. And ln c equals 4. Ln is a fancy way to say log with base e, so let's write it down here. E will become the base for the exponent. E to the 4th is equal to c. And these are our answers written in exponential form. Again, I know we can simplify some of these, 7 squared, 10 to the 5th, e to the 4th, but that's not what was asked. You were asked to convert. Just change the form and stop. Okay? You have to be able to go back and forth between the two forms, because what we want to do is evaluate logarithms. So if I ask you to evaluate log of 16 with base 2, well, I don't know what that is. So I'm going to call it something. I'll just call it y. It's equal to something that I don't really know. So now, I don't know how to do this problem in log form, but I could do it. I could try to do it in exponential form. So if you can't do it in log form, write it in exponential form and see what happens. So that means the 2 will become the base. The y and the 16 switch positions. 2 to the y equals 16. So there's a couple ways you can do this. 16 is 2 to the 4th. Well, then y equals 4. So this is 4. Okay. Log of 36 base 6. Again, let's say I don't know what it is. I have no idea how to do this, so I'm going to switch the form. 6 to the y equals 36. 36 is 6 squared. So y equals 2. That's a 2. Log of 81 base 3. Again, I don't know what that is. So I'm going to switch the form. 3 to the y is equal to 81. 81 is 3 to the 4th. So y is 4. So log of 81 base 3 must be 4. Log of 100. I don't know what that is. But I know this base should be a 10 here. So 10 to the y is equal to 100. 100 is 10 squared. So y is 2. The bases match. Y is 2. Log of 4 base 16. I don't know. So 16 to the y is equal to 4. 16 is 4 to the second. So 4 to the 2y equals 4. There's a power up there you don't see. It's 1. So 2y is equal to 1, which makes y a half. So this is a half. Log of 1 base 5. I don't know what that is. 5 to the y is equal to 1. Well, any base to the power something has to be 1. What is that power? 0. Any base to the power 0 is equal to 1. So that must be 0. So then we'll have 6 to the y equals 1 over 36. Again, I don't know what that is, but I know 1 over 36 is really 36 to the negative 1. And 36 is 6 squared, so that's 6 to the negative 2. So then y must be negative 2. And finally, ln e to the 8. We'll call that y. We'll change ln to log with base e. Now we're going to switch positions. You got to be a little careful. This is the argument of that log. The whole thing's going to the other side. So e to the y is equal to e to the 8. So then y must be 8. Okay, that's what we're going to do. We're going to evaluate logarithms by switching them to exponential form. Here are some properties of logs and natural logs that you should know, okay, preferably off the top of your head, but you can convince yourself of them. We've already convinced ourselves of a couple. The log of 1 with base a comes out to be 0. So I'll show you how some of these work. Just so that you understand. Let's say you didn't know what this was. Log of 1 with base a. I have no idea what that is. So I'm going to switch the form. It would give me a to the y is equal to 1. And I'm trying to solve for y. Well, I have a base to a power. The answer is 1. Well, then the power must be 0. Anything to the 0 power is a 1. Okay. Property 2. Log of a with base a is equal to 1. All right. Log of a with base a is equal to 1. If I switch the form, we'll say it's equal to y. Let's say we don't know it's 1. A to the y equals a. Well, that's a to the first. So what's y? 1. There's my answer. Log of a to the x with base a is equal to x. Okay, so this is like saying, here's an example here. Let's say I had log of 5 to the second is equal to 2. That's what that's saying. Or it's saying 5 to the log of 2 base 5 is equal to 2. If you have a power or a base raised to a power that has a log in it, that has the same base as the base from the exponent, and then you get the answer, which is the argument of that log. Okay? That's what it's saying. And then finally, this one comes from the one-to-one property that we did for exponential functions. If log of x with base a equals log of y with base a, meaning the logs are, you have a log on both sides, both with the same base that are equal to each other, well, then the arguments of each log have to be equal to each other. Okay? On the other side, with natural logs, the natural log of 1 is equal to 0. Again, these are all properties that correspond to the properties on this left-hand side here. The natural log of e is equal to 1. These two you should know off the top of your head. Okay? Without a doubt. In calculus, you use them all the time. You should really know that the natural log of e is 1. You shouldn't need a calculator to tell you that. The natural log of 1 is 0. You shouldn't need a calculator to tell you that. Okay? ln e to the x is equal to x, and e to the ln x is equal to x. All right. Let me just show you here, like property 3, for example. If I had ln e to the x and say I don't know what it is, I'll call it y. ln is a fancy way to say log with base e. Okay. And then if I switch the form, e to the y equals e to the x. So then y has to be x. So that's where we get the x from for our answer. All right. And then if I had e to the ln x is equal to x, right now this is in exponential form. I'm not sure if you can see it. There's a base to an exponent power. All right, let's call this something else. We'll call it question mark just to make it a little bit easier to follow. So this is a base to a power is equal to something. So I'm going to switch the form, but I'm going to switch the form to log form. So I'm going to write log. E is the base of the exponent, so that becomes the base of the log. And then these two switch positions. So the log of something with base e is equal to ln x. But ln x is log with base e. So now the log of something with base e is equal to the log of x with base e. So that something has to be x. That's why e to the ln x is equal to x. Okay, and then finally the same one-to-one property that's down here. All right, so let me show you what we can do with these. So let's say in example A, I'll show you two ways to do this, and then you do whatever way makes you happy, whatever's easier for you, whatever makes more sense. The natural log of e to the 1/2. Let's say I don't know what that is. I'm going to call it y. Okay? You can use the property. There's a property that says natural log of e to the x will equal x. So the natural log of e to the 1/2 power must be 1/2. That's the property. Okay? Let's say you didn't know that, though. Let's say you didn't know the property off the top of your head, and you only knew that it was ln e to the 1/2 equals y. Well, if you don't know something in log form, switch it to exponential form and see what happens. E to the y equals e to the 1/2. So what's y have to be? 1/2. So there's the answer as well. I don't care how you do it. If you memorize the property or you just do it using exponential or switch it to the other form, that works as well. E to the ln 8. We have a property that says e to the ln x is equal to x. So then this is just 8. That's it. Okay? Or you could switch this to log form, which we just did on the previous slide. Letter C asks you for 15 times ln 1, the natural log of 1. The natural log of 1 is 0. So 15 times 0 is 0. Okay? If you didn't know the natural log of 1 was 0, well, I don't know what it is. So I'm going to switch the form. E to the y is equal to 1. What's y have to be? The exponent have to be, to make this answer 1, 0. So ln 1 would be 0. And then d, ln e, that's 1. You should know that off the top of your head. Again, if you didn't, you could say, I don't know what it is. Switch the form. E to the y is equal to e, but e has a power of 1, so y must be 1. Okay? They both work. They both do the same thing. All right, let's try letter E. Log of 3x minus 5 base 2 equals log of x plus 12 base 2. Okay, so these logs, I have equal logs on both sides with the same base. So their arguments must be equal to each other to make this true. So I'm just going to set the two arguments equal. 3x minus 5 equals x minus 12, or x plus 12. So 2x minus 5 equals 12. Add 5. 2x equals 17. X equals 17 over 2. And there's my answer. That's done. Letter F. ln natural log x squared plus 5x equals natural log 14. Again, I have the same log on both sides. These two expressions are equal to each other, then their arguments must be equal. X squared plus 5x must equal 14. So now I have a quadratic. How do I solve quadratics? I move everything to the same side, and I try to factor it. X squared plus 5x minus 14 equals 0. I'm going to factor this. X and x, they have to multiply to be negative 14 and add up to 5. So that's going to be positive 7 and negative 2. So x comes out to be negative 7, and x comes out to be 2. Those are my two answers. Okay, we will have to check logs and natural logs coming up to make sure that their values inside the argument are positive, but we're not doing that yet. It's coming up. Okay, but that's something to look forward to. And then finally, the domain of a logarithmic function. The argument of a logarithmic function must be a positive number. Okay, it has to be a positive number. All right, and we can see why that has to be true. Let's say I had log of x with base a is equal to y, and I switch the form. A to the y equals x. So I switch the form on it. Now, look at where the argument of the log, x, ends up. It ends up over here on the other side. It's what is equal to the base raised to the power y. Okay? But here's the thing. We talked about this before. If you have a base and raise it to a power, all right, and a, okay, is a positive number, but not 1, then you can't get a negative number over here on the right-hand side, no matter what number you put in for this exponent. So the argument of a log has to be a positive value. So for example, if I ask you to find the domain, okay, so the argument, before we do that, the argument has to be greater than 0. Can't be 0. Can't even be 0. It's got to be greater than 0. Because if your argument is 0, you're saying this answer can come out to be 0. We already know it. That's not possible, right? So if I ask you for f of x equals log of x plus 7 base 5 and ask you to find the domain, take x plus 7, set it greater than 0. X must be greater than negative 7. That's negative 7 to infinity in interval notation. Same thing with b. It's the natural log, but it still has the same property. 3 minus x has to be greater than 0. I'm going to add x on both sides just to make my life a little easier. 3 has to be greater than x, or x has to be less than 3. So that's negative infinity to 3, not including 3. That's my domain. And that's it. Okay, so this is an introduction to logarithmic functions, and we'll be using these throughout the chapter. And as always, thanks for clicking.